chapter is going to be about polynomials. Wonky wavy, guys. We are going to talk about all of this. Yes. I'm going to be adding things in all the gaps. So this all is a review from Algebra 2, but I know it's been a hot minute. But everything on this page you did in Algebra 2. Every single thing. So polynomials are where we get these kind of wavy guys. It's going to have a degree higher than 2. Because if it has a degree of 2, it's a quadratic, and that's a parabola. So the degree of a polynomial, does anyone remember what the degree of a polynomial is? The highest exponent. Not physically the biggest, like cubed to the 4th, quartic, 5th, quintic, 8 octic, 6 hextic. We don't usually use the words though. Nontic would be 9. Dodecatic would be 20, I believe. Yeah.
I don't know why that's the only thing I know.
What about 54?
Huh?
What about 2 to the power of 54?
Quintiquarkic? I don't know. We don't typically use the words for degrees higher than 2, like maybe 3. Cubic. We don't usually use quartic or quintic or septic or anything like that. Septic sounds like a medical term. It is a medical term. So our leading coefficient for a polynomial, it's the number in front of your highest exponent. So it's the coefficient, or so it's, I'm just going to put the number, that means number, not hashtag, in front of highest degree term. And we're going to be using our leading coefficient and our degree of polynomials as we're working through sketching things. Because we're going to sketch these today. Because you know a lot more about polynomials than you even remember that you know. Because we've been working with them a bunch. So end behavior is the thing you did in Algebra 2. Yes, sir. No, you don't need to have the graph. I'm going to talk about some things on it, but it's not like super specific. We're going to remember what some of these points are called. We're going to talk about end behavior real quick. End behavior is something you guys, again, did in Algebra 2. It's a way to describe the arrows. It talks about the arrows at the end of a function. And all it is, it's where they point. So as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. These are all the possible options there are. With an even degree function, your ends are going to match. So even degree functions, they both go up or they both go down. They match. It's whether it's a positive leading coefficient, like we have a happy face parabola, they both point up, or a negative leading coefficient, frowny face parabola, they both point down. So for our even degree, they all have arrows very similar to a parabola. So for a positive leading coefficient, the way we write it is as x approaches negative infinity, we usually say f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches positive infinity. So we read the arrow as approaches. We just draw an arrow for the word approaches. So as x approaches negative infinity, as x gets real, real small, my y's get big. As x gets real, real big, my y's get real, real big. With the negative leading coefficient, that's when it has that same end behavior as our frowny face parabolas. They're again going to match, but instead of pointing up, they're going to point down. Come on. So we're going to write it out as x approaches negative infinity. F of x approaches negative infinity. So if we have a negative leading coefficient and an even degree, they're both going to point down. As x approaches positive infinity, f of x approaches negative infinity because they match. So whenever you have an even degree function, it's going to be one of those two. It's either going to be positive or it's going to be negative. Only options. It's a little bit different with our odd degree terms because odd ducks like to go to the disco. So one goes either way. Odd ducks go to the disco. And the way that I think about it and keep it straight is I think about a line. If a line has a positive leading coefficient, positive slope, it's going to go like that. My left arrow points down, my right arrow points up. So an odd degree function is going to have the same arrows. As x approaches negative infinity, f of x approaches positive leading coefficient. It's going to look like this. So left arrow is going to point down. This is fancy schmancy math talk for left arrow down. And our right arrow, as x approaches positive infinity, if we have a positive leading coefficient and an odd degree function, my right arrow is going to point up. So f of x approaches positive infinity. They point in opposite directions, and our leading coefficient tells us which way they go. For our negative leading coefficient, whoop, we switch directions. As x approaches, that's a weird arrow, negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches negative infinity. These are the only options for end behavior. Those are the only choices. Yes, dear. Yeah, I can scooch it up a little. Sorry, it's going to make it real, real tiny, and I can then adjust it. Boop. There we go. So there's my odd degree function and behavior. These are the only options for end behavior on our polynomials. So for polynomials, this is it. The only time it's going to ever have anything different is if we have a limit that's a constant. It would have a different end behavior. Okay. So a couple of other things to remember. In our polynomials, the way that we're going to be doing polynomials, they're always going to be continuous. We're not going to have discontinuities in the polynomial. Like, we're not going to have holes. Not until we get to rational functions. But then we also need to remember our extrema and our roots. So I'm going to say this guy and this guy are going to have the same kind of title. What kind of point are they? Maximums. These are relative maximums. These are relative maximums. Why are they not absolute maximums? Because there's not a very maximum. Does this polynomial have an absolute maximum? No, because it continues on forever. What is this point down here?
Minimum.
The minimum, our absolute minimum. How about this guy and this guy? Relative minimums. Relative mins. Let me get another color. Let's go. I'll go with yellow. How about these yellow points? What are these yellow points? The roots, or our zeros, or our solutions, or our x-intercepts. This one is a little different. What's different about this one? Does anyone remember? For this green one. It's
a double.
It's a double root. It's its own little baby parabola. So whatever that root is, let's say it's 2. X minus 2 squared. So we're pretending it's 2. All these others are single roots because it passes through. So maybe that one's 3. I could write that as x minus 3. I could maybe write this one as 4. X minus 4. So we write our roots just like we did for parabolas. It's just when it has a bounce like that, it's a double root. It just means that piece is squared. Yes, dear? This is our absolute minimum because it's the very, very bottom that it goes. It's absolutely as low as it goes. Yeah. All right. So again, these should all at least be vaguely familiar. Hopefully relatively familiar. Haha. Put-um-bum. Because what we're going to do is we're going to identify a whole lot of pieces about these, and by the end of the day, we should be sketching them from equations. All right? Ready? I was like, I know there's a lot of stuff on this page. That's why we only have 3 more slides after this, because I knew this slide was going to take us a long time. We have 4 problems where we're going to do 2 of them are sketches. So we're going to do 2 where we identify pieces and 2 where we sketch the whole thing. Okay. Ready? Boom shaka. I'm going to just zoom it in so we just see one at a time. That's the one we're looking at first. F of x equals 5x to the 4th, 3x squared, minus x plus 1. So f of x equals 5x to the 4th plus 3x squared minus x plus 1. And my first question is, what is the degree? It's 4. You are exactly right. Where did I put my stylus? There it is. How do we know it's 4? It's the highest exponent, so my degree is 4. What is my leading coefficient? 5. It's that number in front of that highest degree term. So now here's something I haven't mentioned yet today. What's my y-intercept? 1. You remembered. Is this guy at the end? That's our y-intercept. We can also write that as 0, 1. It'll ask us what the constant is. That's that same one. It's the same one. So if they ask you what the constant is, this is the number added on the end. Yes, sir?
So you want y-intercept as a
I recommend putting your y-intercept as a point.
constant, just a number?
Constant's just the number. That's the difference between the two. I'm not super petty if we say the y-intercept is 1. Since it is a y-intercept, we know the definition of a y-intercept. It's fine. It's just one of those, why are we asking the same question twice in a row? I just put 1 as a point, 1 as a number. Because otherwise it's the exact same question. So then what we're going to do is we're going to find our end behavior for this equation. To find our end behavior, we're going to look at our degree and our leading coefficient. Our degree is even or odd? Even. Our leading coefficient is positive or negative? Positive. So if we are even and positive, I know my end behavior. Evens work like parabolas, so they're going to match. Positive is a happy face parabola, so they're both pointing up. So the way we write our end behavior is just like we wrote it on that first page. As x approaches negative infinity, I usually do my negatives first. It is not a math law. It's just organization. I didn't think left to right. As x approaches negative infinity, f of x approaches positive infinity. Left arrow points up. As x approaches positive infinity, right arrow, f of x approaches positive infinity. So left arrow up, right arrow up. I keep trying to drink out of my coffee cup and it's empty and it's making me sad. Okay, we're going to do the same thing with g of x. So we got g of x is negative 2x to the 5th minus x cubed plus x squared minus 4. So on g of x, what's my degree? 5. What's my leading coefficient? Negative 2. What's my y-intercept? Ooh, that's not the highlighter. So my y-intercept, 0, negative 4. Or the constant being negative 4. It's the same thing. It's just looking at it in two slightly different ways. So to find my end behavior, I need to know, is my degree even or odd? Odd. Is my leading coefficient positive or negative? Negative. So that tells me my end behavior. as x approaches negative infinity, this time it's called g of x. I'm going to say g of x approaches what? Left arrow points which way? Up, positive infinity. As x approaches positive infinity, g of x approaches where? Negative infinity. Okay? Feeling okay on end behavior? Because we're going to smash it together with a whole lot of stuff. I know my handwriting looks trash on that page. I'm sorry. Switch it back to fitting full page so I can zoom things in and write neatly. All right, ready? So we're going to identify all these pieces and we're going to sketch it. So the first thing I want to know, and this is going to feel like a trick question, what's my degree? If I was to multiply this out, what would be my biggest exponent? I heard it once. 3. X squared and another x. So when it's in factored form, you got to count how many x's there are. So there's 3 as my exponent. So then we asked, what are our zeros? What are our roots? 4 and negative 2. What is my leading coefficient? 3. If I was to multiply this all out, the only thing in front of my x cubed would be this guy up in front. So my leading coefficient is 3. We can actually still find our y-intercept even when it's in factored form. We take all the constants up there and multiply them together. Let's try writing things down, not doing it in our head. Because what we need is I need that 3 out in front times the 2 that's been squared times the negative 4. So what is our constant? Negative 48. Ooh, that was a bad 4. Let's try writing the 4 again. Which means my y-intercept is 0, negative 48. So I don't have to multiply it all the way out to find out what my constant is. We can take all of our terms and kind of smash them together. Yes, Jan?
How is the degree
Because I have, x squared times x. So if I was to multiply it out, it would be x squared times x, which would be x to the 3rd. So and I could rewrite this equation as 3 times x plus 2, x plus 2, x minus 4, right? 1, 2, 3 x's, all being multiplied together. And if it helps, absolutely feel free to write it like that. Totally fine. Absolutely. All right, so now we're going to write out our end behavior. I'm going to erase that, just a piece of equation there. Because I'm going to need that space in a second. To be fair, I don't have the last one on my screen, so I don't remember. So we have a degree of 3. Is that even or odd? Odd. Do we have a positive or negative leading coefficient? Positive. So we have an odd positive to find our end behavior. You've written it down for surezies at least once. So odd positive end behavior, that's like a positive slope line. As x approaches negative infinity, f of x, yeah, we're f, approaches what? Negative infinity. As x approaches positive infinity, f of x approaches positive infinity. So we're going to put all these pieces kind of onto a sketch, and then we're going to find out we do need one more piece of information. Yes, dear? We're going to use it often enough that you probably will. I'm not going to ask you to like just spout them off and just like, burp. But if we remember how they're related, it's... So let's put the things we have kind of on our sketch. I know we have a y-intercept at negative 48. So we know it's down here somewhere. It's a sketch. That's an 8. I have roots at positive 4 and negative 2. What's up? 0, negative 48. It's my y-intercept. I just took this guy and I wrote it over here. For my end behavior, I can put that up here. I know my left arrow points down and my right arrow points up. But I'd really like to know when things are above my axis or below my axis, right? That would be really, really helpful. We have done that when we did quadratics and our inequalities. Or we'd make our little table of our factors. We're going to do this thing again. Remember this guy? Where we would take our roots, where we have our negative 2 and our positive 4. And I'm going to take my factors, my x plus 2 squared and my x minus 4. F of x. And I'm going to say, if my x values are less than negative 2, is x plus 2 squared going to be positive or negative? So if I have a negative 3, it's going to be positive. If it's between negative 2 and 4, is x plus 2 squared going to be positive or negative? Positive. If x is bigger than 4, is this going to be positive or negative? Positive. So this guy, it's been a minute since we did it though. If my x's are less than negative 2, is this chunk going to be positive or negative? Negative. Negative. If it's between negative 2 and 4, is this positive or negative? Negative. If it's bigger than 4, is this positive or negative? Positive. So my function, if it's less than 2, is this positive or negative? Negative. If it's between negative 2 and 4, is it positive or negative? Negative. And if it's bigger than 4, is it positive or negative? Positive. What this tells me is that this side of 4, it's going to be below. So over here, I mean, you don't have to color the whole thing in. I'm going to get my way bigger highlighter. Down here, it's going to be below my x-axis. It's never going above over here. No, I'm just pointing it to you so we can draw. We're going to do a sketch. You don't need to color the whole thing in. This is just so I can show you where this is going. To the right of 4, it's going to be above. You don't got to color the whole thing in. All we got to do is connect it up and make sure my line stays in my highlighted regions. You don't have to do the highlighting. It's just so that we can show it. So I'm going to connect from my arrow to my 2, and it's got to stay here. So it's going to have to turn around. Go through this, go through my 4, and hit my arrow. You see why I did the coloring thing a little bit? You don't have to have it. Like, that's our sketch. This was just a tool so we could see what the positive and negatives were trying to show us. Okay? You can probably get a pretty decent sketch without this table, but it's one of those things we're going to use it coming up later on, so we're going to practice it now when it's a little bit silly to do so. Okay? We can also see what happened with this double root. We got this bounce because we had to stay negative. That comes from the fact that this guy was squared. So it bounces off that. It's a double root. So even if we didn't catch that, doing our positivity helps us figure that out. Okay? We're going to do one more like this. But any questions on this first one? Sweet. This is the last one for today. So we have f of x equals negative 2 times quantity x plus 1, quantity x minus 3, quantity x plus 2 squared. So first things first is what's our degree? 4. Because I have x times x times x squared. So there are 4 x's here. Where are our zeros? 3, negative 1, negative 2. Because our degree is how many x's are there? There's x times x squared. So x times x squared times x squared is x to the 4th. So there's 4 x's here. What's our leading coefficient? Negative 2. So then we're going to try and find our y-intercept. That's our next step. So to find our y-intercept, we take every constant up there. We're going to have our negative 2. Let me change colors here. Negative 2 times 1 times negative 3 times 2 squared. We take all the constants, including the leading coefficient. Oh, I should put it on the constant line, but whatever. So what are we going to get? Because we have positive 6 times 4. So we get 24. So our y-intercept is at the point 0, 24. So shoot, we can even come over here and put that on our little sketchy sketch. Our y-intercept is positive. We know it's up there somewhere. So then let's do our end behavior, and then we'll do our positivity. So our end behavior, is our degree even or odd? Even. Is our leading coefficient positive or negative? Negative. So we have an even negative, which means my end behavior is going to be what? As x approaches negative infinity, f of x approaches which way? Negative infinity. Left arrow points down. As x approaches positive infinity, what happens to my right arrow? Goes to negative infinity. Yeah, because they're always going to match. Even degreed functions are always going to have matching end behavior. All that means is I have an arrow on the left that points down. I have an arrow on the right that points down. We do know our roots. I can throw those up on my little sketchy sketch. I know I have one at -2. I have one at -1. And I have one at +3. It's a sketch, so scale is relative. And that's great, but I'd really like to know which side of my axis things are supposed to be on. So let's do our positivity real quick. So we're going to take all of our pieces. I'm even going to include my leading coefficient on this one. So we've got our roots. -2, -1, and 4. So our -2. Oh, you're right. It's 3, not 4. Thanks. I'm going to take my other factors, my x plus 1, my x minus 3, and my x plus 2 squared. There we go. So when we have a negative leading coefficient, that is negative the whole way across. So it's going to play games with our signs. So make sure to include that when we're looking at our positivity. X plus 1. If x is less than -2, is this positive or negative? Negative. If it's between -2 and -1, is this positive or negative? If it's between -1 and 3, is this positive or negative? Positive. And if it's bigger than 3, positive. For our x minus 3, if it's less than -2, is this positive or negative? If it's between -2 and -1, is this positive or negative? If it's between 1 and 3, or -1 and 3, negative. And if it's bigger than 3, positive. How about for our x plus 2 squared? Positives across the board because it's being squared. No matter what's inside, since it's being squared, it is positive across the board. So when we're looking at our function here, getting our positivity, we're multiplying the whole way down. So negative, 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 positive. Is this positive or negative? Negative. So I know that to the left of -2, it's staying below that x-axis. How about between -2 and -1? Is it positive or negative? Negative. So it's again below my axis. How about if we are between -1 and 3? Positive. And we're going to go ahead and hit our y-intercept while we're up there. Boop. And our last section is going to be negative. So it's going to go boink, down like that. So that's another way to kind of think about it, so you can see all the pieces without having to use a highlighter or anything. I just wanted to kind of see the regions. But that is the first half of 4.1. I'm leaving this up for a second, but I do have the 4.1 homework written on the last page. So you can start homework 4.1. Okie dokie, okie dokie. It's only 7 questions. I think it's actually not brutal, because I went through and I removed some of the superfluous questions. It only took me 2 pages. So I got a Johnny answer key for it. It's not one of the 5 pages. Only 2 pages.